Very good morning to everyone. As part of continuous improvement, I decided to develop an automotive ECU, which means like demo automotive ECU for training, because till now, over the period of 4 years, whatever that we did is just like the simulation sort of the things. We use a software to synthesize ECUs and message transmission, everything. But we don't want to stop there, as it is a time, everything need a time to move to a different direction. We have achieved to that, we have come to that direction now. So what we are going to do is, now we are going to develop an awesome automotive ECU from the scratch. And then slowly we are going to expand the training coverage to the new level. Right now, till now we just use the software to understand and hear things. Now we are going to have our own demo ECU. My aim is not to sell the product to the end customer or to sell it to the market. First, we have to have a very good prototype to explain things to the candidate. We have already have a proven record of conducting system training for the very long period of time. Now we are entering into prototype development. So in that, as a starting point, let us do from the beginning, and then let us do it from the scratch. We are going to have our own footprint in this one right now. So I have some 60 to 90 days of time to complete this one. As a day-wise goal, we will move towards that development. I want to update what I am doing with respect to this one as an insight for you people to have similar thoughts, and I want you also to see how the development cycle works from the beginning, product development cycle, like how they are doing it, those sort of things. I am trying to put everything into a very process oriented thing, but there might be, because it need a time for us to get a master in this field, because as far as the system testing training is concerned, we have a clear roadmap and clear that is curriculum and everything. But for this one, we have to yet to derive those things, that we are going to do it via this development. Okay, no. So first thing is the agenda for this 90 days or this development cycle is developing a demo automotive ECU for training. We are going to have our own ECUs to create a real CAN network. It is not like only in software. We are going to have our own real network. That is the aim, initial aim that we are going to have. For that, in order to achieve this goal, as a day one plan, what I decided is I want to choose a microcontroller for ECUs, and then are we going to use a inbuilt CAN controller, inbuilt CAN peripheral microcontroller, or external standalone one, for the sake of availability and cheapness and that is easy programming environment, availability of programming environment. Based on that, I choose this one right now. This is already many people in the internet have done to some level using this big microcontroller. They try to bring a CAN controller, CAN network, but that needs a lot of improvement. It is very in a basic level. Based on the experience that we have, I am trying to expand it to the next level. That is the plan. Yeah, that's why we are choosing very cheap components. Instead of saying cheap components, we can say like the components which plenty available easily. The availability of them is very easy, and then the development cost will be very less. Instead of going for other things, from my view, this is the choice that we have. And then as far as the programming knowledge is concerned, programming language is concerned, we have chosen embedded C. Using embedded C, we are going to do that one. right now. So this is the components and tool that we want to use in this development. The next step is the initial design. So initially we plan nearly 4 ECUs in the network. For a prototype things, we are going one by one. Like initially we want to have minimum 2 ECUs going to be there in the network. So that is the aim. And we have selected the external CAN controller, external standalone CAN controller, because the availability of PIC controller with this inbuilt CAN controller, CAN peripheral, that is not available in the market. Very what is the easy availability? Otherwise, ease of access is not available. That's why I have selected the standalone one. Also, many people have started developing their own CAN network using this one. So, as we want to follow the same path and want to use the same path to achieve what we want right now, because somebody has tried already. So we are observing and developing our own right now. So that's why we have selected this microcontroller, CAN controller we have selected. So the interfacing between the main controller, which is a PIC controller, and this CAN controller will be they will communicate each other via serial peripheral interface. So as we have a SCI, a CAN, LIN, we do all have serial peripheral interface to interface the peripherals with the microcontroller. For that, we are going to use a SPI. SPI will be used to interface with the CAN controller from PIC right now. That is the aim. This is a high-level initial design that we have. We have to add more point to this, but this is the basic design that we have as of now. Then, when we want to do a development, first we have to start the work in steps. We have to ensure that we have all necessary tools and controllers available for the ECU design. And then we have to try some sample programs in that microcontroller. And then only we can go to the next steps. As a first steps, because this 16F887, no, that is very new to me. And I previously worked with 16F877A. And this is then another controller. So as we are using in this one, we are going to try a simple program in this PIC controller initially. For example, using a LED toggling or something like that. Again, so we can design our own circuit and proceed. As initial assistance, my plan is to use a development board. When I was doing my MTech, in that time I bought a development board, PIC controller board. I'm going to use that one to initially validate that my program that I am developing using embedded C, that is the program that I develop using embedded C, can be flashed and executed in this controller. That is the first test that we want to do, whether we are able to do a small LED toggling like that. There are you can argue like we have a Proteus and other software to do the what we are designing, but my thing is I'm not happy or I'm not agree with doing things in software. The problem behind that is you won't have a real hand in the ground. Otherwise, you're not scratching the ground. It's just everything is an imagination, or everything is an ideal condition. But when we come to real-time implementation, only then we will come to know what are the challenges that we have when we try to make a product right now. That's why my aim is do it in the ground. I stand in the field and then find out what are the challenges that we have. We will address that one by one and achieve what we want. Right now, that is our goal. The next step is that's what the development board I am going to create a small program in embedded C, and I want to flash that one in that controller. I also want to execute that one right now. That is our aim. For that, as far as the programming environment is concerned, we have a MPLab XIDE that is freely available, that we can get it from Microsoft Microchip website, right? My MP Microchip website, we can get that IDE, and then now we can start writing it. It's very easy process, and I did that one yesterday. I am not going to explain how to install this one, this tool and other stuff that we can cover later as improvement or otherwise add-on session. As of now, I have installed this MPLab IDE, but it is very easy. I don't find much challenge in installing that one. After installing that one, I started writing a simple C program, embedded C program for toggling of LED. So in my development board, the development board that I have, in that one, I have an LED in RD. So that means port to D second pin. Right now there, they have connected the LED and it is available in the development board right now. So this is the LED. See here. Right. Right. This one. I'm going to toggle that LED. Right. And then this is the program that I have written to toggle that LED. For that, initially, there are some configurations that we have to do for every controller. For example, watchdog timer to disable the watchdog timer and the burnout reset, those sort of things. These are the configuration that we have to do every controller. These if you don't do these configuration, your controller may not work as expected. So it is very important that you can change the behavior of the controller using this one. That is one thing. And this one xc.h is an header file. Sorry, embedded C in MPLab IDE. So that I have here. These are the configuration that we have to do in order to work with that particular controller. What are these configurations? These are a preprocessor configurations that we have to do every microcontroller. This is applicable to every microcontroller, like watchdog, disabling watchdog timer, and then turn on the brownout reset. Those things we have to do. To do that, they have provided you a GUI. You can just select the setting that you want in that GUI. Then they automatically generate the pragma codes. You can simply copy those pragma codes and paste it here. In order to get that GUI, go here and then set configuration bits. Here you get it. Here they are saying like FOC oscillator select bit, that an RC oscillator. That means those sort of selections that we have to do. And then watchdog timer. I think I disable the watchdog timer here. And then power up timer. Power up is that is disabled here. And then brownout reset, that is enabled. And then low voltage single supply, that means serial programming, that has been enabled, right? Low voltage programming is enabled. And then data EEPROM memory code protection bit, that is off. And then flash memory write enable bit off. And then flash memory code protection bit, those things are in off state. After doing it, hit this generate code to output, you will get that one. Then you paste that here. So now we have the configuration, pre-process configuration is done. After doing it, we are including the header file for embedded C. After including embedded header file, we are having here we have function declaration, that every functions will be declared in C before main, and then they will write the descriptions. So that declaration has been done here. Then we have main function. In main function, we have we have some piece of code initially the first line of main function is stress D. That means now we are assigning 0 to the something called a variable stress D. Right now we give that value to that one. But actually this stress D is a register in PIC microcontroller that is used to configure port whether they are input or output, because the port pins in microcontrollers are configurable. Using this configuration register, you can configure port D pins. I configure port D pins as output. Why I am doing it? In my development board, I have a RD2 as pin RD2. We have connected a LED. Right now, we are going to toggle that one only. That's why I assign trusty value to 0. That is the first step. After doing it, we create, there is an infinite loop. This is same for every program. Every embedded program will be in a continuous execution. That's why they have infinite while loop. Inside that one, we have I am toggling port D bits is the object, and then in that RD2 is a child, which is nothing but in port D, I say I complement or I toggle D2 pin, RD2 pin. So I simply toggle the RD2 pin after making a complement. After doing it, I call it delay. This toggle delay is a function. This function's going to produce a 25 millisecond delay. For that, we have written a function description here. Inside this function, initially T1con is another control register in PIC microcontroller. It is used to configure timer 1. So timer 1 control register is set with the value 1. What it means? So if you take, like, let me copy this T1con, and then I come back to data sheet of that. Yeah. So this is T1con register. This is the explanation from the data sheet. Here we set only this bit. We are making these bits to 0. So when we make this bit to 1, what it means really? Actually, it means we are enabling the timer. We enable the time, and then we just keep the rest of the thing 0. When we keep the rest of the thing 0, what it really means? So here it is 0, timer 1 gate is active low. That means, sorry. Yeah. So it is set as 0. After that, timer 1 gate enable bit. So that is also 0. Timer as it is this bit, when that bit is 1, gate enable bit. Actually, that if that bit is set to 1, timer 1 bit is set to 1. If we have is on, if timer 1 gate is not active, timer 1 is on. I think this is another bit that we initialize with 0. Then we have a prescaling bit. As far as the prescaling is concerned, as we loaded 0 there, we are not doing any prescaling. That means we are not dividing the clock further. Then we have LP oscillator in a control bit that is set to 0. LP oscillator is off, and then here the synchronized external clock input, that is also 0. So I think we are using internal clock. That's why it is set to 0. And then clock source select bit. So as we are selecting internal this bit to 0, so they are using internal clock. We are not supplying the clock from the outside. Then we turn on the timer. Those are the configuration that we do using this first instruction. After that, we are loading some value. That means timer on high, timer on low. In that, we have loaded 30D4. How we arrive this 30D4? Actually, it is a timer 1 high byte and low byte right now. So for that, there is a calculation. It is like it is creating 25 millisecond delay. How we come to know that it is creating 25 millisecond delay? That is, they have a formula for that. To the parameter of that formula is oscillator frequency. In our case, it's 20 megahertz. That is the board that we have development board that we have, no, that is using 20 megahertz clock. And then prescaler value, we set it to 0, so it is 1, there is no prescaling. And then the tick is computed by means of 1 by, that means the prescaler value 1 divided by the oscillator frequency divided by 4. Why we are oscillator frequency divided by 4? Every microcontroller will not use whatever that you supply using the clock. So the crystal oscillator, they will divide that frequency by 4. So 20 megahertz divided by 4, our microcontroller is operating at 5 megahertz speed. After that, the delay expected is 25 millisecond in our case. For that, I have a thing here. Then the counter value is computed, that is in seconds. The counter value is computed by means of the delay expected divided by the tick value. When I do that, I get 30D4 right now. So that is actually, this is counter value in decimal, counter value in X. That is what loaded here, 30D4 right now, the timer counter value. After doing it, I again enable the timer, otherwise I start the timer. When I start the timer, it will, after counting for a period of time, there will be a overflow. It may reach the count value. No, the moment it reaches the count value, that means 30D4, they will set a flag in the interrupt control register. There is a global interrupt control register in microcontroller. In that, we have a timer interrupt flag. For any timer overflow, they will set that flag to 1. If it is 0, they are counting. The moment it becomes 1, they come to the next line. In that next line, we we stop the timer and then we clear the flag, because we are going to do it, we are going to enter for the second iteration. Right now, we clear the timer, we stop the timer and then we clear the flag. After doing it, again we come for the second iteration. Again we toggle the dedo bit and wait for a delay. Again toggle the dedo bit and wait for a delay. Like that, we are doing it forever. That is the program written to generate the X value, X file. For this, we have to build that. We can just right click and select build here. So the build is successful. The file is ready right now. Now we have to flash. In order to flash that one, I have a flasher PIC2 installed in my laptop. So let me open PIC2 now. So they are storing the file here. This is the location, right? So PIC phone and not connected. That means we don't have any microcontroller in place, right? So I just place the microcontroller from the board, motherboard to flasher now. Done. After doing it, I ask for reading. When I read that, they are saying this is the PIC controller, and these are the configuration and other stuff they are saying. After doing it, I just want to write my program, and in order to write that, I have to load file now. So import X. I go to the direction. That means the path that I copied here. This is the path. Right. In that folder, I have a X file. Right. I select that X file and I just to open that. So they say some configuration what's not in the X file, like that they are saying, but it's okay for me. So I loaded the file now. This is time for flashing. To flash that, I just hit write. So the flashing is over. Now it is time for us to close this one. I close that. So Now it is time for us to, I connected the controller in the board. It is toggling. Let me show you. It is toggling. Let me show you that it is doing in the. So here it is. Maybe you may not find the toggling, right? It toggles. Okay. From this, we conclude that our board is working. Our board is working. And from this, we can proceed to the next level, like implementing other things and do that one. This is the day one plan that I completed. As of now, that I'm able to work with my microcontroller board. I'm able to write a small program with that program and I can execute in the controller. If this is achieved, we can go for the next step. What can be the next day plan? Day two plan. Day two plan is very simple. We are going to implement the SPI in the controller. We are going to serial peripheral interface program, and we are going to try to write something, and then we also we are going to see whether we are able to write something using SPI and how that works. So by connecting MCP 2515 as a slave, we are going to connect PIC microcontroller with its slave, right? And we are going to write something. That is what we are going to try. That is the day two plan. Okay, team. With this, I end today's session. Let me catch you with more detail in upcoming session. Thank you. Thank you for watching.